Welcome back, everybody. So we're in section 9.4, which is titled The Radius of Convergence. And so we're going to kind of extend our understanding of the interval of convergence using this idea of radius. But more importantly, we're going to start focusing on different tests we can use to determine the convergence interval for a particular power series. So we'll just note above here that if we're thinking of interval of convergence, which we've been working on, with geometric series and other power series, the interval of convergence is that interval where the infinite power series that we have is representative of some other function. So if we have 1 over 1 minus x equals 1 plus x squared, etc., this entire infinite series is going to represent our function on the interval -1 to 1, meaning 1 over 1 minus x and this power series are exactly the same on that interval. So what we do with radius of convergence is we simply kind of reorient how we're describing the interval itself. So if A is the center, then the radius, again, is the distance from the center to the end of our interval. So instead of doing, 1 is less than x is less than 3, what we can do is we can say that we can simply say that r is equal to 2. Right, meaning the distance from the center is 2. So if we had, say, the interval of convergence 1 less than x less than 3, we know that our center is going to be at 2. Right? So 2 is the midpoint between 3 and 1. So our radius is equal to 1. So again, radius is just going to be the distance between the center of our power series as well as the endpoints. So it's going to give us the distance from the center where we're going to have convergence. So there's 3 possibilities. So we could have a finite number. So we could get divergence, obviously. So this means the series may or may not converge at either endpoints, but we know that all the values are going to be greater than some value r, so we can have divergent series, obviously. If we converge for every x, then r is going to be what we call infinity. So this is like e to the x, sine x, cosine x. Right? Those are series that converge everywhere. And again, for number 1, if we're on the interval of convergence, then we're going to be less than r. So we're going to be on that interval smaller than r. And so this would be like the geometric series. Geometric. Convergent. Or we're going to be completely divergent except at the center. So this is convergent at the center only. So this means as soon as we move away from that value of a, our values blow up, and we get a divergent everywhere series except for at the center. So those are going to be kind of our 3 possibilities. We'll be on a closed interval between a plus or minus r. We'll be convergent everywhere, or will only be convergent at 0. Sorry, at the center, which means our radius is 0. Okay, so let's kind of look at what we've looked at so far. So the geometric series test, obviously, we've used quite a bit. So we can find the convergence of a series and its sum by computing s is equal to the first term over 1 minus r. And the interval of convergence, of course, is going to be, in general, the absolute value of r is less than 1. And for a generalized power series, if we have x minus a to the n, let's say, then the interval of convergence is going to be a plus or minus 1. So a minus 1, a plus 1, and the radius will equal 1. Now, if we manipulate x minus a, it'll change things as well, so we can shrink and stretch the interval of convergence. But for our generalized geometric series, our radius will be 1 if it's just simply a linear transformation. All right, so the nth term test was something we also talked about, which had to do with the limit of the sequence of the series. So if a sub n diverges, one way to determine divergence, so we could again think of this as the divergence test. So we use this to test divergence. So if the limit of the sequence of terms is not 0, or it is non-existent, then we have a divergent series. So keep in mind, however, the other way does not work. If the limit, as it says below here, is equal to 0 for the sequence, we cannot determine convergence. So the limit being 0 is not sufficient for convergence, but it's necessary for convergence. All right, so necessary, not sufficient. And so our counterexample to that, of course, was the harmonic series. Right, so the harmonic series has a limit of the sequence being 0, but the sum being infinite. All right. And then also the direct comparison test, which we talked a little bit about. We didn't do too many examples with, but this is going to be nice, where if we have a nice convergent series that we know of, we can use it to bound our series that we're considering. So if b sub n is above a sub n for all of the terms of the series that correspond, then the series will converge likewise. So essentially, if we can bound it above by a convergent series, then we get a convergent series. And note, we cannot have negative terms for this, so it can't be an alternating series. And conversely, if we have a divergent series and we show that it is somehow below another series that we're considering, so that meaning that it's unbounded by the divergent series, then it will also be divergent. So direct comparison test is going to be very useful, in particular with p-series. So p-series is going to be the most common application. So let's go ahead and see if we can look at some of these to see if we can determine convergence or divergence. So we've got a number of examples here, and I'll let you maybe pause the video here and go ahead and give them a try. So for A, we can see that those leading degree terms are going to matter for our sequence. So if we take the limit of the sequence, we can see that this is going to equal negative 1/2, which is not equal to 0. So by our nth term divergence test, the series diverges. Okay, so that's the first thing that I would say for any series to look at, which is the limit of the sequence. So ignore the series expressions and the values themselves. So, don't write out what all the values are going to be and kind of look at how the sum is working or anything like that. Just look at the limit of the sequence of the expression, right? Because if we take the limit of the sequence and it's not 0, then we're definitely going to be divergent by that nth term test. All right, so for B, we can see this looks like a geometric series. We can maybe simplify it a little bit. So we can see the limit of the sequence is going to 0, and we've got an exponential expression. So we just need to manipulate this so that we can determine exactly what the expression looks like. So we'll want to keep the 81 over 16 here, and then we'll kind of equate powers here. So I'll make 3 to the n plus 3, 3 squared times 3 to the n plus 1, which means we'll get 1 over 9, and then it'll be times 2/3 to the n plus 1. Okay. And so note, this is going to be a geometric series. With r equal to 2/3, which is less than 1, thus the series converges. And for this type of geometric series, I'd probably have you calculate the sum as well. So you might want to maybe do that off to the side and figure out what the sum of that geometric series would be. We'd probably want to reorient the expression a little bit more. So like we could cancel the 9 and the 81, which would become 9. And then the n plus 1, we'd probably want to change to n maybe. But we wouldn't have to for the first term. So again, you could work out what the sum is equal to on your own there. All right, so for C, this one looks kind of unfamiliar. Note, if we take the limit as n goes to infinity, it'll go to 0, because the linear term n grows faster than the natural log, obviously. The natural log grows very slowly. So the limit of the sequence is 0, so that's not going to help us. But what this almost looks like is the harmonic series. So this is where the comparison test is going to be useful. So for our comparison test, let's go ahead and look at what we can use for our comparison test. So let's compare this to our harmonic series. Okay. So note the natural log of n for n equals 1, well, that's 0. And then n equals 2, that's going to be slightly less than 1. But if I get to n equals 3, the natural log of 3 is bigger than e, so that'll be slightly larger than 1. So as I go further and further out, the natural log of n is going to be greater than 1 for n greater than 2. Right, so this will be true for all values of n greater than 2. Thus, this series is going to be less than, oh, sorry, not less than, oops, bigger than. All right, so I'm going to have a bigger number on the left than I will on the right for every term n greater than 2. And so we've got an infinite number of terms. So by the comparison test, since the harmonic series diverges, also diverges. So again, our series also diverges. So for the work, we just want to show some inequality and justification here. The inequality will typically be enough because it'll be pretty obvious. But a lot of the comparison test will be with this harmonic series. All right, so for D, now we've got x to the n over n factorial squared. So this one's very different than the other ones. We've got a power series now, and we've got n factorial, etc. So there's a number of ways we could approach this, but this one I also want to use the comparison test because this series looks very, very close to another series, which is x to the n over n factorial. So take a moment and think if you can remember the exact series that represents. And yes, this is e to the x, right? This is our e to the x power series. So the power series x to the n over n factorial is convergent for all x. And we can see here that this series has an extra n factorial term in the denominator, meaning it will be smaller. For every comparative term, it will be smaller. For any value of x, it will be smaller. So this is less than the series on the right, which is a totally convergent series. So by the comparison test, since this series converges everywhere, so does our original series here. So again, bounding below by a convergent series versus bounding above for a convergent series and then unbounding it below, essentially. So again, for C, we showed that the series on the left is bigger term by term when compared to a divergent series, whereas for D, the series is smaller term by term than our convergent series. So again, this showed that we are unbounded, and this shows that we are bounded. All right, so those are kind of our initial tests that we started with, that we kind of looked at. Didn't do too many examples with, but we'll start working on more examples now. And what we're going to need to do now then is add some additional tests for convergence. So one is the ratio test. And that's going to be kind of our main test, the ratio test, but we'll also have a root test and an integral test. But for 9.4, the focus will be on that ratio test. We're also going to define absolute convergence here, which is a different way of showing convergent that's a little bit stronger than just saying that a series is convergent. So we'll pause the video here and then we'll finish the notes in our next